In this video, I'm going to show another strategy that students use in Unit 3 to help them solve equations. And I'll be looking at lessons 7 and 8. And the strategy is using a hanger diagram, very similar to a balance scale or a hanger, where we are trying to keep the scale balanced. And I'm going to model just two examples here on the hanger and equation matching section. So I'm going to use A and B as my model, and I have that pulled up here on my paper. So I'm going to make this nice and big so we can take a look at it. That first example is a hanger balance that shows some number of value on the left and then some unknowns and a value on the right. And the goal is to keep it balanced. So as we're working through equations, we're constantly repeating and reminding the students that the whole concept of solving equations is keeping things balanced. So if I want to try to figure out what the unknown numbers are, I can eliminate or take some things off the scale. So we would say, I know that this is a value of 1. So if I remove this 1 from the scale, my scale is going to be off balance. This side's going to be heavier. But if I remove a 1 on either side of the scale, then I have 3 W's or 3 unknowns. And I don't know what they are, but there are 3 missing numbers on this side. And then I have a total of 1, 2, 3, 4, 5, 6 on this side. And we might even have students redraw. But for now, I can just show you that they're combining what they know and combining what they know. Some teachers may even have them write the equation up at the top. 6 is equal to 3 W's. 3 what's? And at that point, we would help them see that each one of these W's is going to be split between this number 6. So 3 times what is 6? W would be 2, because 3 times 2 equals 6. Again, a very visual way of representing equations. And if we were to write this as an equation, what we actually originally had were 7 ones on one side, so 7, and that would be equal to 3 W's plus 1. So again, we're helping students understand just a basic equation, how we can represent it visually. All right, so on this side, we're going to take a look at another one, very similar. And so we have students say, what do you see? Like, what do we see? We have 2 Z's, and some students even like to write it. We have 2 Z's, and we have 1, 2, 3 ones. And on this side, we have 1, 2, 3, 4, 5 ones. And again, some students like to write the equation up at the top so they can see the equation and how it represents the hanger balance. So what can we do? What do we know? We know that if we take 1 off of the left side of the scale, in order to maintain that balance, we have to take 1 off the other side of the scale. So the left and the right, 1 from each side. I can do that again, and I can do that again. So when I took the 3 away from each side, I ran out of 1s on this side. I still have 2 over here. So what I now have is 2 Z's are equal to 2. So again, we're doing the concept or the process of solving equations, which is what they will eventually do regularly, taking 3 away from both sides. And even sometimes we'll model the algorithm or the math with the balance scale. I took 3 away from both sides, and that left me with 2 Z's, and that would be equal to 2. And at this point, we're doing that inverse operation. 2 what make 2? Well, 1. So in this case, the 1's are 1. So Z would be equal to 1. Okay? And to check this, they can actually go back and make these 1's. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. On each side of the scale, I have 5, so I know my Z is equal to 1. Again, the hanger balances are just another visual to help students solving equations. In this example, I'm getting from the lesson 8. So if I click over here to lesson 8, we're going to look at how we can use the distributive property and write equations using the hanger balances. So I'm just going to do 2 of them here. And I have a 14 on this side. And on the other side, I have an x and a 3. And another x and a 3. So I actually have 2 sets here. And what we would do is we would have students maybe circle and say that I have an x and a 3 and another x and another 3. So using that distributive property, we could help them see that this is 14 equals 2 groups of x plus 3. Now, some students may like to redraw and group my x's with my x's and my 3's with my 3's. Very similar to what we did with tape diagrams. So some students may even come inside here and like re-sketch it, and sometimes I'll even tell them use a different color so they can kind of see. I can sort and put my x's with my x's and my 3's with my 3's. And then they could write that equation, which is 2x's plus 6. Either way, they can solve the equation. Okay, so now they don't even need to use the equation to solve this. They can take 3 off of each side of this scale, but they have to take both 3's off of this side of the scale. So they can either use their group here and take 6 away, or they can take 3 off of each scale. So now I know that if I take 14 and I subtract 6, that leaves me with 8. So sometimes they'll even write 8. Sometimes they like to redraw the scale, but 2 x's would equal 8. And sometimes if it gets a little messy, teachers may say, come over here and rewrite it. So this is what is left. And 8 is equal to 2x. And 2 times 4 is 8. All right, this last one, again, we have an x and a 5, and we have another x and 5. So sometimes teachers will tell students to group them x plus 5 and then another x plus 5, and that is equal to 16. Again, they can redraw it, and again, we can leave this as 16, but we could organize this as x and an x, a 5 and a 5, which is 10. So now my equation's a little bit easier to solve. So I can say, all right, well, I can take 10 off the scale, but I also have to take 10 off the scale here, which is going to leave me with 6. So now, instead of having that big 16, I just have 6. So each x is going to be divided by 6. 6 divided by 2, and that would equal 3. So x is equal to 3. And they can come back into the original problem, and they can plug a 3 in for each x. 3 plus 5 is 8. 3 plus 5 is 8. 8 plus 8 is 16. Or they could come here and plug each 3 in for this. 3 plus 3 is 6, and 6 plus 10 is 16. So hanger balances are an excellent way for students to practice solving equations, and they're very closely connected to the tape diagrams.